Hi folks, welcome to 4.7 Applied Optimization Problems. In this video, we're going to take a look at the 4.7 practice, and we're going to go over question number 1. So let's read it. Question number 1 says that a rectangular garden is to be constructed using a rock wall as one side of the garden and wire fencing for the other 3 sides. Given 200 feet of wire fencing, determine the dimensions that would create a garden of maximum area. Then determine the maximum area. So what we're going to start off with here is a diagram, okay? I find it really beneficial to start all optimization questions with a diagram. So in my diagram, I have this rock wall. And on that side of the garden, I'm not going to need a fence. But I do need fence on the other 3 sides of this rectangular garden. So like here, I'm going to need a fence, here I'm going to need a fence, and here I'm going to need a fence. So all the parts in the pink are going to be wire fencing. And we're going to go ahead and label this. So I know that I have a side over here. I'm going to call this Y because it's vertical. Not super creative, I know. But I can also say that the corresponding side of the rectangle is also going to be Y. And then the last side in the pink, I'm going to go ahead and call that X because it's horizontal. All right. Now I know based off of this that I have X and Y as the wire fencing. And just to kind of preview ahead a little bit, I know that I have 200 feet of wire fencing. So we're going to come back and use that information in a bit, but right now we're going to focus on writing our main equation. And so our main equation comes from what is it that we're trying to maximize? So in this case, I am trying to maximize the area. And so because I'm trying to maximize the area, what I'm going to do is write the area formula for the shape that I've drawn. And so I can see here that the area of a rectangle is going to be length times width, or X, times Y, using the variables I have from my diagram. Now this is what we are going to find the derivative of. All right. Now, one thing that we need a little bit of help with, though, before we write our derivative, is we need to think about having only one variable. And let's talk about why. The reason I'm only going to need one variable is because right now I have an X and I also have a Y. And in Calc 1, we only know how to handle situations that only have one variable on that right-hand side. And right now we have 2. So our job is to make this equation. Okay, so we want to find the derivative, but first we want to make it a single variable equation. So we need to come up with a single variable equation. So that's fancy math speak for saying we need to get rid of the X or the Y. One of them has to go. So let's go back to that wire fencing information and see what we can do with that. So earlier, I said that we have 200 feet of wire and we know that all the parts in the pink are wire fencing. So another way we can say that is that X plus Y equals 200 feet because all of the things in the pink are the wire fence. And we can even condense this to be X plus 2Y equals 200, okay? Now, what I'm going to do is I'm going to take this equation, I'm going to solve for one variable, and then I'm going to substitute it in to my area equation, okay? So right here, let's say that we're going to isolate one variable and then sub into area equation. Okay? So, let's see. I see x plus 2y equals 200. I'm going to take the easy route here and just subtract the 2y to the other side so I can get x all by itself, and then I've isolated one variable. So I've got x equals 200 minus 2y. Now what that means is everywhere that I see an x in my area equation, I'm going to go ahead and put 200 minus 2y. Okay, so that again is going to go right over here where the x is in the area equation. So let's go back to our area equation with our new substitution. So now we can write that area equals not x times y, but 200 minus 2y times y. And since I know I'm going to need to find the derivative, I want to see if I can simplify first so I don't have to use too many of my fancy rules. And so what I'm going to do is I'm going to distribute this y to both terms in here. And I'm going to get area equals 200y minus 2y squared. Now that looks like an equation that I can take a derivative of. So now we're going to go ahead and find that derivative. dA dy equals, the derivative of 200y is just going to be 200, minus the derivative of 2y squared is going to be 4y. Now the special thing about maximum points or minimum points is that the slope there is 0. So we can say that dA dy equals 0 at our maximum. And now we're going to solve for y. So I get 4y equals 200 and y equals 50 feet. Okay? So let's see what we found so far. We have found the y value of the situation. But we need to find the dimensions of the garden, which means we need to find the x value as well. And then we want to actually find out what is that maximum area. So let's go ahead and see if we can find the x value. So to find x, we're going to use x equals 200 minus 2y, that equation that we had put in the yellow earlier. And instead of y, I'm going to write 50, because that's what I found earlier. And when I clean this up, I get 200 minus 100, or x equals 100 feet. Okay? So if I think back to my diagram, if I have a y value of 50 and then an x value of 100, I'm going to maximize that area. So for our last step, let's go ahead and find the area. Okay. So let's circle this back up here. To find the area, all we're going to do is plug in to our original formula. Area equals x times y. Or we could say 100 times 50. And we'll get an area of 5,000 square feet. That's going to be the maximum area that we can have in our garden based off of the amount of fence that we have. Okay? So, before we leave here, I just want to put up a diagram that might help us visualize this a little bit. Okay? So if you go to Desmos or your graphing calculator and you graph a equals 200y minus 2y squared, okay, you should get a picture that kind of looks like this. All right, you've got your axes, and then the graph looks something kind of like this. And the maximum point here has a y value and a, because we're using y to represent the single variable and our area is our resulting. And the coordinate of that point, based off of what we found, should be 50, 5,000. Okay? And that just helps us solidify that the length of y should be 50 and that the area should be 5,000. All right, so that's a really good way that you can check your answers, is once you have your formula, graph it on Desmos or a calculator to see whether or not you're getting the correct point at the end of it. All right, so we're going to stop here for this video. All right, let me just zoom out for a moment so you can see the whole screen. And in the next video, we're going to talk about question number 2. All right, see you there.